Now let's look at this formula. This formula tells us something about the rate of decay, right? Rate of decay or activity. We can call it activity A, and is given by lambda m. This is a decay constant. And this is the number of nuclei present. Number of nuclei present, meaning this is the remaining nuclei. So it shows that this rate of decay is directly proportional to the number of nuclei present, right? So from here we want to do some mathematical proof. Okay, from here if you do differential equation, we rearrange all the n to the left hand side, and then we set some boundary. Let's say the boundary is from n naught to n, meaning from the original amount to the remaining amount, from time 0 to time t, any time later. So what we solve here is you integrate 1 over n, you get ln n. Because you get ln n, and it has to be from the boundary n naught to n, so this lambda t, the t is from 0 to t. So what you have here is a ln n over n naught, and then you have t, lambda t. Okay, do not forget the negative sign. So what you have here is, if you want to get n over n naught, you're supposed to make e negative lambda t. And because of this, you can make a general expression for number of nuclei remaining using this expression. Okay, so this is what we call the remaining nuclei. But if you want to find out the number of nuclei decay, you have to use another type of expression. That will be this one, equals to this minus this. This is a remaining one. Right? So you can derive further, but you can derive anytime. You don't have to memorize this. So that will be the expression. 1 minus E, get this. So activity and decay constant. In a random process and spontaneous process, the rate of decay, radioactive decay, negative d and dt of a radioactive sample is directly proportional to the number of radioactive nuclei present. So that's the conclusion we can make. And since we know that molar mass big M and mass of the radioactive nuclei can be related by N equals to mass over molar mass, and N equals to number of nuclei over Avogadro's constant. Okay, therefore it's concluded that we can also write this expression in this way. Why we can make such conclusion? Because M is proportional with N, and N is proportional with big N, so directly related. You have this. Because of this, I can make this conclusion. Remember just now we have the formula, this number of remaining nuclei. So even the mass can be written this way. mass, the remaining mass, equals to original mass times exponential negative lambda t. If you go one step further by writing A as the activity, A is lambda n, the activity. Okay, remember to put a negative sign. So if you have n equals to n dot e negative t, negative lambda t, if you set it as negative dn dt, you will have differentiated this expression, so in respect to t. So you integrate this expression, you bring negative lambda to the front and not, and this expression, if you look carefully, is actually original activity. Okay, if you put the negative sign to the other side, of course. If you put this here to the other side, so you get this and A naught and E negative lambda t. So this is what we call activity of the sample, and this initial activity. Initial activity. And this is the activity of the radioactive nuclei after some time. We also can find this to be acceptable. C as the count rate. And this count rate is recorded by the detector, and this count rate is proportional with activity. Therefore, we can also write the count rate as count rate and then E negative lambda t. So this is the initial count rate of the radioactive sample. Okay, so we can have so many expressions that we can just write a general expression of this. Okay, where x could be activity, could be mass, could be number of nuclei, could be count rate, and x naught could be all the initial condition of all these parameters. And something worth noting is the activity is given as the unit becquerel, then m is kg or g, and then number of nuclei is just number of nuclei, and count rate is some of the books written there count rate as curie, but it's not really used anymore.